Echo, stop.
It's just so strange.
And I think you have then when, Paul, you then have to spotlight me because at the moment it switches to wherever the sound comes from.
Yeah, just looking.
The crew not satisfied just leaving this local bluff though. They vote to go further. The local bubble is a large.
You are. Okay, it's 3:10, I reckon, by my time. Good afternoon, everybody. Welcome to the G-QRP knowledge share session with Mark MM0DQM, who's going to talk about his experiments with loops and milliwatts, which sounds very interesting. So we'll just get underway in a moment, just joining some more people.
Yeah, Paul, if you could mute everybody except
I have
myself.
done, yes.
Yeah.
I have done.
Just £6 a pair with prescription
trial.
coatings included. That's select spec style at selectspec.com.
Okay, Mark, you're okay. I've muted everybody. Hopefully, I haven't muted you.
Okay, so I think
Okay.
I think we can start then.
Okay, I think we'll start. Yes. So
Yeah.
welcome, Mark, then to talk about living experience with milliwatts, QRP knowledge share, and if there's a chat window, and if you want to ask questions as we go along, we'll try and get around to covering them as we go or at the end. Over to you then, Nick. Okay, Nick.
Oh, it's Mark. I was thinking, okay.
Oh, sorry,
so,
Mark. Yes, sorry, Mark. Yes.
Fine, no problem. Good afternoon, everybody. And yeah, welcome to this afternoon session. Just a few words about myself. My name is Mark, greetings from Scotland. That's where I live at the moment. And I've been a radio amateur licensed since 1985, but started with an interest in radio since fairly early childhood. And when I got licensed, initially my main interests already were using the computer for amateur radio, wrote one of the first software packages to do facsimile transmissions with amateur radio, and so on. And then after a break, a few years ago, I went back into the hobby. Very happy about that. And I'm now a fairly young member of the G-QRP club, YQRP. I really enjoy it, working with low power and trying to bridge larger distances and use software and computer technology in some ways to find the needle in the haystack. And my presentation this afternoon is going to be a bit about that. So just share the screen. So I'm going to talk about my magnetic loop experiments with milliwatt QRP. So just an overview about what I'm going to talk about. Give a brief introduction about magnetic loops in general and their physical and electrical characteristics. Then I'm going to show you my experimental magnetic loop design. So I built a magnetic loop specially for experimentation, so a lot of parameters can be changed, parts replaced without a lot of soldering. I'm going to mention a project that brought me to actually the whole subject I'm talking about, the Australia project, where I first came across the use of Raspberry Pis in amateur radio as a whisper beacon. Talk about my setup, how I do operate the setup, and then the results of the experiments that I did both with Whisper and the Raspberry Pi Zero, as well as FT8, the FT8 experiments I did with my FT818 transceiver, SAM the QRP range, and some web resources, and of course, space for questions in the end. So what are the characteristics of a magnetic loop antenna? I guess most of you came across them, but just as a brief reminder about it, the important thing is I'm talking about resonant magnetic loops here, because there is some loop antennas used for reception that are not resonant. They are basically just a wire loop connected with an amplifier to a receiver. We have a resonant magnetic loop here. And what are their physical characteristics? One important thing, at least for me, is they are of a fairly small size compared to huge antenna towers. They are portable. You can easily carry a loop around. If it's made out of coax wire, you can even put it in a backpack and take it wherever you want. They're fairly inconspicuous. So, I mean, on one hand, they are eye catchers. They can really look beautiful, but on the other hand, they're not always in the garden visible for everybody in the neighborhood. And all in all, magnetic loops are very well suited for what I call the small QTH, the small property with a smaller garden where you cannot set up antenna towers or even long wires. So that was what raised my interest in this type of antenna. What are the electrical characteristics of a magnetic loop? So that is completely different subject here. The main aspect of a magnetic loop, of a resonant magnetic loop, is it is a resonant circuit. So we have the coil and we have the capacitor, and both are tuned to the resonant frequency you want to receive or you want to transmit. And if you use a magnetic loop for transmission, it is important, as we have a resonant circuit here, to acknowledge, even with QRP levels, sometimes you can get fairly high voltages across the capacitor. Even with a few watts in the QRP range, you can get a couple of 100 volts across the capacitor of the loop, and the coil emits or has a magnetic field, a fairly strong magnetic field when transmitting closely around it. I'm saying this not only from the technical side, but a little bit as a disclaimer. I mean, this is interesting experiments. They're in no way dangerous, but if you have a cardiac pacemaker or a defibrillator, I would probably take care experimenting with this type of antenna, particularly tuning them manually. That means being fairly close to the whole antenna system. So that's the magnetic loop as a resonance circuit. Then the next aspect is magnetic loops are not omnidirectional, they are directional. What you see here on this slide is a simulation I did with, probably a lot of you use Phonic2 for antenna simulation. And you see the characteristic figure of H-shaped pattern, transmission pattern around this loop antenna. So when you set up a loop, expect the strongest transmitting directions basically in the vertical plane, in the same plane as the loop coil is oriented in space, which gives it, and you can see it in the result later, quite a directional characteristics. Then loops have a fairly narrow frequency response. And we are not talking about megahertz, we are talking down to kilohertz, less than 100 kilohertz here. The graphics you see on the slide is the same simulated loop, but that you see the strong peak. If we have, for example, a loop antenna for 40 meters, you have only a peak a few kilohertz wide, which gives the magnetic loop both a huge advantage for QRP and a disadvantage at the same time. The advantage is because it's so narrow, the frequency response, you get much less noise on the loop, and it's very efficient. On the other hand, it excludes certain modes or makes it fairly difficult. Like, I think FM is fairly unsuited for use with magnetic loop antennas. And another aspect, we come back to this later, is you have to tune a magnetic loop really precisely if you want to get maximum transmission power out of the antenna. So now we come to my own magnetic loop design. What I wanted was something that is portable. I said this already. I want to have a versatile design. And that means I want to have a loop that I can run in different loop configurations. I want to experiment with like having 1 or 2 turns. I want to change the capacitor and see how does the loop differently react to different capacitors. There's vacuum capacitors, there's air gap capacitors. So see that. And there is the whole another field of experimentation about the feed. How do you want to feed the antenna from the transmitter? So that's I hope I'm back online. I just noticed I was muted accidentally. So these are the main points of the magnetic loop design I wanted to create. So let's have a closer look at the various elements of the loop that I designed. We start with the capacitors. I had the luck on an amateur radio flea market to get this really beautiful vacuum capacitor that is not just a really good capacitor for a magnetic loop, but it looks fairly good as well. So I took that capacitor, polished it, put it in between 2 brass plates, and made it in a way that it can be connected to the loop. And on these slides, you see that that's another aspect of my experimental loop, that everything can be connected together. So the main loop is made of copper pipe, and it can be connected to the capacitor through PL259 connectors. You may notice on the slides that there is no center pin there. There's 2 different reasons for this. One reason is the center pin isn't needed, and because of the skin effect, most of the transmission or power of the signal is going through the outside of the loop. And the other thing is more a practical one. I soldered the PL259 sockets to the brass with silver solder. This required quite some solder power, so I had to use a torch. And we all know PL259 plugs, the inside is plastic. You do not want to have a smelly experience, so I punched that out before doing the soldering. On the right-hand side, in the plastic container, you see a standard air gap tunable capacitor, like you find it in old radios and so on, that I use as a second capacitor for tuning. The advantage is it has a higher capacity, so works fine on the lower frequencies. And another thing, if you look on the top left, bottom left picture here, you see in the background these 2 plates, copper plates connected, and that's an additional capacitor I made. It's just 2 copper laminated boards spaced by nylon screws to build an additional capacitor that I can set in parallel, particularly with a vacuum capacitor. So that allows me to tune the loop for the 40-meter band, for example. So here we have the capacitors. Come on. And now let's have a look at the feeds that I'm using on the magnetic loops. The standard feed I'm using, particularly when running Whisper, is a simple copper coil, what you see on the left picture. The feed point itself, the design is a bit different. What I did, and it actually brought some advantage to the whole system, I didn't just connect the feed cable to the loop, but I put matching capacitors in between, tiny tunable 250 picofarads variable capacitor, and with a switch you can put another 100 pico in parallel, so you can put an optimum match on the feed loop to get the best signal. On the right-hand side, the loop you see, the feed you see is a so-called Faraday feed, which is basically the same 1 coil of wire for the feed, but this time with a coax braid around it, but only connected on one side, because otherwise it would short circuit the whole thing. I've seen discussions on the web whether these type of feeds are more efficient or reduce noise or not. My own experience with Faraday feeds is that they bring a slight advantage in terms of noise reduction, but on the other hand, you pay for them with slightly reduced transmit power. I mainly come from, you probably see this in this presentation, from an experimental point of view. There's probably a lot of things people can calculate and do a lot of maths about, but I enjoyed just building this and experiment with it and see what happens. So here you see the whole kit. That's just all in all arranged on one picture. So on the left-hand side, this is basically an easel, you know, what you use for painting that I sometimes use as a tripod. The advantage is it's completely non-magnetic and non-conductive, so it doesn't influence the magnetic field on the loop. 2 clamps to connect everything to the easel. And then the others on the right-hand side is the stand that I use to set up the loop. And in the center, you see 2 coils of copper wire that can be used for the loop and the various feeds and capacitors. So what we basically have is a loop kit here that can be easily assembled, disassembled, or operated in different configurations. Oops. So now let's have a look at what I said initially at the Australia project. So I had this loop, and then suddenly I'm a member of the Hackaday IO Hackers and Makers website project. So I'm registered there. I came across G7CKF's Australia project. So Jenny List tried with this project to build a transmitter with a Raspberry Pi. And her idea was, is it possible to use a simple Raspberry Pi and transmit and get the signal heard at the other side of the world? So the main goal was going all the way to Australia. But what I see here, at least she managed to get to the United States. And the antenna in use was a wire antenna. I think she put it in the attic somewhere. And when I saw this, I was thinking about, oh, that's an interesting project. So how about combining a Raspberry Pi transmitter for Whisper with a magnetic loop and do the same long-range transmission experiments, but with a setup that is much smaller and portable? So that was the inspiration. And I started after this to build a Raspberry Pi Whisper beacon with a magnetic loop. So here we have the circuit design on this slide. And you can see, I mean, it's the setup you find in many Raspberry Pi Whisper configurations. You have the 7-pole Chebyshev low-pass filter. I talk about the filter later because a lot of people think magnetic loops are narrowband antennas. So why have that filter in place? It's a waste of components. I'm in a different opinion there, and you will see why. Here you have the matching setup with either just the variable capacitor, or you can short circuit everything. So you have the feed loop directly connected to the output of the filter, or the additional 100 farad. And here to the right, that is then the resonant magnetic loop. So that's the whole circuit, all on a neat little circuit board. And as you can see on the picture on the left, it just gets strapped to the pole that holds the magnetic loop. So yeah, a few words about filters. So people think, on one hand, when talking about using Raspberry Pi digital outputs to create and transmit signals for amateur radio, you always need the low-pass filter. And I completely agree with that because it is a square wave output, and because it's like the clock, one of the clock oscillators on the board of the Raspberry Pi. And that means you have square wave, lots of harmonics there. What has happened now? I will be back in a second. I just lost the screen share. One moment, please. Something was wrong here. What is happening here? Here's something wrong. Paul, there's somebody on the screen. I'm no longer spotlighted. You are viewing Colin 9H4CT's screen. So I'm the one who has to be spotlighted and the only person with the permission to do screen sharing.
There we are. I don't know quite.
Okay, so I'm back. I just have to. So where we were here about filters. So yeah, a few words about the filters. So we see on the picture on the right-hand side, there is a lot of harmonics in the output of the Raspberry Pi. And the thing that mostly worries me is the peaks and harmonics between 100 and 150 megahertz. There is even one pretty close to the international aircraft distress frequency that somebody really doesn't want to transmit about. It looks to me screen share is gone already. Paul?
Yes, I'm working on it.
You've booted me out again.
I didn't.
Can you make me simply co-host, because then you can do with the participants what you want. And
Okay, Mark, I've made you co-host. I don't know
you.
what's going on there. Can you screen share now? Yes. Sorry.
So we have these harmonics, and on the left-hand side, you see the output of the Pi with a filter. You see, and there's nothing more on the higher frequencies. The reason why I advise to use the filter is if you look at the magnetic loop, basically all the loops together, not as the resonant, but they are quite a sizable antenna, even if you compare it like to a telescopic antenna of the same length. So you can have unwanted transmissions from a magnetic loop antenna. So that's why I would say definitely use the filter if you want so. Here an overview about the whole design again with labels. So how I built it and the sizes. So the feed loop 27 centimeter diameter. It was all made of 8mm copper pipe. Main loop 86 centimeter diameter. And then we have the capacitor, the vacuum capacitor, and for 40 meter, the copper laminated boards to add as an additional capacitor if you want to do so. So how to operate the setup? Pure thing about that, at first avoid any metal objects near the loop. It was very interesting when I was working with the magnetic loop to discover how easily, because of the sharp resonance peak, a magnetic loop can get out of resonance. You see that bicycle on the slide, and I put it there exactly because of that. I once had a case where there was a bicycle standing nearby, and I was wondering, I actually had a network analyzer connected to the loop, why is the reading so bad? And it was indeed the rim of the wheel that was acting like a short-circuited coil and completely detuning that loop. So it's important that you avoid any metal objects near the loop, no radiators, no bikes, no cars. And with near, I mean within the next few meters of the loop. The setup is powered by a USB power bank. I used it particularly for experimentation to make sure that no RF gets into the mains or whatever, that I can be sure everything is just transmitted out of the loop. The Pi is remote controlled via secure shell over a Wi-Fi connection, which is fairly easy. Just you log in from the computer. The only problem there is sometimes when the thing transmits, the shell connection isn't working. It could be something that the electric or magnetic field of the loop is basically stuffing the Wi-Fi chip on the Pi, but usually it comes back shortly after each transmission period. And time synchronization is essential, which means you have a connection either to the internet or through a mobile, so that the Pi gets, the clock on the Pi gets well synchronized. That's important for Whisper. I wrote a little script that actually not just when you start the Pi, but even when every couple of transmission sequences, it resynchronizes the time to stay in synchronization. And a few words about tuning and matching. Tuning a loop on low power is tricky. You cannot use high power equipment on the one hand. On the other hand, the problem is that everything that gets close to the loop has an influence. So I'm using two ways of tuning the magnetic loop. One thing is what you see on the left, one of these dip meters and absorption frequency meters. The scale is not accurate at all, but for things like tuning a loop antenna, it's ideal. You see the reading on the meter, and you can give it a coarse tuning. And for the fine tuning, I use that little ICOM receiver, hold it close to the loop without an antenna attenuator enabled, and put it where a bit of a signal minimum is, and then tune the capacitor. So it is a bit tricky, but in the end you get there. So now let's have a look at the results. There's some experiments with 10 milliwatts on 20 meter. On the left-hand side was a recording I did in 2018, and what you see on the right-hand side actually was yesterday, where I had the loop set up and did some transmissions. One important thing you will notice is it all goes like in one particular plane, like from the northwest to the southeast. And the reason for this is the directional characteristics and our QTH. We have two hills behind the house. And if I want to do some kind of transmission, I have to find a position that I can basically, that the main output of the antenna goes between the hills, which is in that direction. So for 10 milliwatts, this is quite a good result. And it's even better if I say the loop wasn't standing outside, it was just standing upstairs in the room. And I got that result. So fairly good. So I can say magnetic loops for QRP is well suited if you want to experiment with things like this, getting like spots from all the way from Northwest Iceland down to Italy. So that's not bad. And here another experiment I did a couple of years ago, this time with 2-watt Whisper on 80 meter with additional capacitors and 2-turn loop. I wasn't expecting a good result because magnetic loop antennas are not very efficient in the lower frequency bands, but at least spots from Germany, from Scandinavia, from Northern Ireland, and down in England. So there were some spots available. Here we have FT8, both on 30 meter and 20 meter band with 2 watts from the FT818. So again, not bad signals all the way from Murmansk on this plot that is PSK Reporter down to the coast of Tunisia. At one point, I managed to even get down to the Canary Islands and get reception reports from there. Yeah, we're coming to an end now. Some web resources. I'm not sure. I guess that the presentations and the slides and things will be shared on the web later on. So there's my project page on Hackaday.io, the Australia project page on Hackaday.io, where you get the software on GitHub if you want to use a Raspberry Pi for Whisper. And the page on the bottom, whisper.fggsde, is a very good page to get an overview about whisper spots, and it's a bit more detailed and a bit more information and statistics than the standard WhisperNet page. So that's just the overview of the presentation. So yeah, thank you for listening. And I think it's now 20 to 4. We just now open for any discussions and any questions. Thank you.
Thank you, Mark, for that. Really interesting. I'd never thought of actually plugging a Raspberry Pi into an aerial via a filter and getting it to work. That's very interesting. So we've got the first question from Dave, N8SBE. He asks, did you measure any difference between the vacuum variable and the air gap capacitor?
It is different to compare them because I mainly used them on different bands. One big difference was, so I couldn't measure any difference in power, I have to say, because it was difficult to measure. The other problem was the tuning. The vacuum one has the advantage because of the screw you have inside the vacuum capacitor. You can really fine tune it and find the gap of the, not the gap, the peak of the resonant frequency, while with the air gap one, at least the one I have, there is no gears, so I have to be really, really careful to find the spot. So I mainly use the air gap one when I do experiments, mainly 40 meter or even lower, and for the rest I use the vacuum capacitor.
Okay, thank you. Somebody would like to know, this is Myron Y03ITI. How critical is the shape of the loop? I assume it is quite difficult to achieve a perfect circle while dealing with copper tubing.
The shape isn't actually that important. You find loops in all different kinds. I've seen loops hexagonal, I've seen square loops. I haven't done any tests to see if there is any difference, but I have to say, I think the shape doesn't matter a lot because you find different kinds of loops. I would probably not use something very oblong because that can change if you go in that direction, more in an oblong shape or something. It can change the electrocharacteristics considerably.
Okay, another question from Roland, AE6VL. Have you tried remote tuning using a motor to drive the capacitor? Not
yet. It is my plan. I actually have a plan not to use a motor, but to attach or to build a capacitor that can be servo controlled with just two copper plates moving in and out. It's one of the plans. For the vacuum capacitor, this is tricky because the tuning, because of the vacuum inside, requires quite some force. So you need a fairly solid built thing in order to tune a vacuum capacitor properly.
Okay, and there's quite a few questions, Carl, N0ICR, and other people asking about using coax or LDF for the loop material. Any comments on that?
I think a lot of people use coax, and I think it's possible because if you use the braid and if you use a coax with quite a tightly woven braid where you have many strands in the braid. I know sometimes you find mainly for audio setups coax with not a lot of strands in the insulation in the braid, but I think RG58 and all these things, it should work well. What matters more than I think the make of the coax is how the coax is connected to the capacitor. So you want a really low resistance connection there. I know you get some magnetic loops where you have like banana plugs and you just put the cable in and you tighten it, I think that won't give you good results, because the magnetic loop isn't only just high voltages. There's considerable currents running as well, and you want to have as low resistance as possible for these currents.
People have been asking about flashover using air gap capacitors, but I mean, I would imagine that's probably not a problem because the power levels you're using is so low.
That's another advantage of QRP. You have no flashovers. I didn't have a single one. I mean, I operated just at QRP ranges, maximum 5 watts. I mean, the FT818 does a maximum of 6, but because I use the output in continuous wave, so I say, okay, go maximum 5 watt, leave a bit of a reserve, and never had a single spark.
Phil asks about the possibility of using multiple loops rather than a single loop. Have you ever thought of that?
It is possible to do that. I mean, one arrangement, and I think the RSGB even had that at one point, is to build a loop in the shape of a figure of 8. And it is a bit tricky to explain. You have basically 2 loops connected together. Yeah, like a figure. It is a twisted loop like a figure of 8, and where they cross between them, you have the capacitor. So it is possible to use multiple loops.
And Alvy Street asks, have you ever tried transformer coupling using a ferrite?
Not yet. Not yet.
So it goes on the list of things to do.
Oh, yes. I've tried gamma matches. That's the other one with the sliding. I built another loop for 6 meters that was on one of the first pictures, but I didn't have any success with that. So it's more like a windowsill ornament at the moment.
Somebody asks, would a partial metal shield not covering the Wi-Fi antenna for the Raspberry Pi help, or would the metal box upset this loop? So metal inside the loop.
Yes, it will. Because if it's bigger metal, particularly if it's like one solid piece of metal, it will have an influence. And what I do to avoid the Wi-Fi and the whole thing, Wi-Fi being clogged up, is just connect the cable and put the Raspberry Pi outside the loop.
And Carl M0ICR asks, what subtunable bandwidth do you get?
It's difficult to measure. It's difficult to gauge. I mean, it's usually less than 100 kilohertz.
And that's why FM is not a good choice.
No, no. I mean, it's ideal for digimodes and CW, of course, but for FM, you can forget it.
Certainly. I mean, somebody else, Alvy said that, Alvy Streeter said they get, with like 5 watts, they get flashover on a 3 meter loop. And my experience with loops, I had problems with flashovers until I had a little capacitor as well. So it's a Raspberry Pi, because it's so low power, it's not a problem in that area.
No. But even, I mean, I did like FT8 with 5 watt and tried experiments and pushed it, but I didn't have a single flashover here.
Well, any more questions on chat? Could you, Mark, could you post up on chat the links that you had on your webpage? Just so
yes, I can do that right now, of course.
Thank you.
So where's the presentation? I hope it copies them properly. Go here. Everyone in meeting. So here we go.
Well, thank you very much then, Mark. Has anybody got any questions they'd like to ask? Another question's come in. Bruce explored the use of a 57 centimetre bicycle wheel for a 20 metre loop. Apparently it's in Radcom, and very pleased with the results. How much effect does the bolted connection to the capacitor make? Oh. Sorry, Mark, your muted. Just a moment. Are you okay? Can you speak now, Mark?
Yeah, yes,
Oh,
I'm
sorry,
here.
yes.
So I just see this question, the shape of the coupling loop. Yeah, that is a actually very interesting subject, because you can change the shape of the coupling loop for matching, because it changes the impedance. And I've seen that they've done that. You can either squeeze the coupling loop or pull it apart. And if you do not want to use a matching capacitor, the same is the distance to the main loop, or even the angle to the main loop. All this can be used for matching the coupling loop with the main loop.
Somebody asked about experience with using Alpex heating tubes. I'm not sure what they are, but
No idea about that. It probably depends on what material. I mean, if it's copper, it looks like Alpec looks like aluminium, and aluminium is definitely not as good as copper. So I would say better.
I think there was a question about what material we use for the loop, and that's copper. I think it's got to be copper, isn't it? Really?
It's got to be copper. I mean, ideally, I would have the whole thing silver plated, but that's not possible.
Okay, if there's no more questions, I'll close the meeting. Oh, just a quick question then. Florin, Y04XPF, how important is the position of the capacitor, up or down?
It doesn't matter. I mean, the position is the position always of the capacitor should be like the opposite. If you use a coupling loop for feed, on the opposite side of the feed. But if the capacitor is down or up, doesn't matter. It's a matter of the whole mechanical setup. I've seen loops with a capacitor on top. I know there's even some quite commercial loops you get where the whole loop bends aside and the capacitor is on top. Doesn't matter. The important is the position of the feed in the whole setup.
Okay, well, thank you very much indeed then, Mark. If there's no more questions, I'll bring the meeting to a close. And
yeah, thanks for hosting, Paul.
Well, thank you very much. That was interesting, very interesting indeed. Goodbye then, everybody.
Okay, goodbye.
You're getting a lot of thank yous, Mark.
I see that. Thank you. Thank you, everybody, for listening.